All right, I think we can get started. All right, we'll get started. What we're going to talk about today, we're now reaching, if you like, the last part of the course, in that we have covered everything we need to about radiation in terms of this module. We've talked about the production of X-rays, the interaction of X-rays, the measurement of X-rays, and we've talked about things like DRLs, exposure indices, and all those sorts of things. So it would be prudent to think, I think, that your exam paper would actually house a fair bit of that previous information. On your exam, there will be 2 questions. You'll do both. You won't have any choice. There's nothing that gets people's attention like talking about exam papers. There will be, I just further to that question, I just checked what the exam questions were. And you can bring a calculator if you like, but I don't think there'll be much need for too many calculations. There will be essay-type questions. They'll be covering, you'll be able to get an excellent mark on sort of giving me back what I've been giving you. So as long as you understand the lectures, you should be fine. I would hope in the last class, depending on how quickly we get through these remaining topics, and there isn't that much more to do, although there's a bit today that will take a bit of effort. I would hope that in the last, I reckon my calculations are that we have 3 classes left. I would hope in the last one that we will have time to address any questions or queries or problems that you have. The aim of that particular class will be, particularly I hope to give the last hour at least of the final week to us going over the questions. If not, we'll get another tutorial or whatever. But the aim will be that you will bring whatever questions you have. If you don't bring any questions, it'll be an extremely short hour. So it's up to you guys to bring any queries, any questions, any problems. Specific. Don't give me things like, can you explain radiobiology to me? You know, just if you can have sort of precise questions that we can actually get through, that would be good. Yeah, so the paper will be 2 essay questions. With every exam, to state the obvious. You know, don't be afraid of saying the simple, easy, straightforward things. That's where usually most of the marks are. And then get into the more complicated things. If you're going to draw diagrams, give half a page to a diagram. And the best advice I can give you for preparing for exams is go through the old papers, you know. Go through all the old papers, because I'm not that smart that I try and create new exam questions every year. You know, will rely at least in part on old questions. If you know the old questions, you'll be fine. Yeah?
Do we have access to the old papers?
Yeah, you should have access to all the old papers. If they're not available online, then come back to me and I'll get Debbie to put them up. In terms of your assignments, by the way, Debbie apologizes profusely for not getting your marks up. I spoke to her yesterday. I know a number of you are waiting for these. I know that half of them have been done, and she's just trying to find a minute to do the remaining half. But as I said, you've all passed, you've all got good marks. It's just, I know you're anxious to get the actual mark, and you will have that very shortly. Yeah? Yeah. Okay. Well done. All right, let's keep going then on the digital image. This is something kind of different from anything we've talked about. And a lot of this nowadays will be very sort of obvious to you guys because you live in a digital world. But it will give you a grounding, I think, of what some of the other subjects will lead you into in the next this year and next year. So we're going to go through some obvious things and then get into some sort of details that I think are going to be useful to you that you may be less familiar with. But the bottom line is, in this country, I don't think we're using film in any more than about 5 or 10% of locations. So we're predominantly using digital in the vast majority of situations. Where you might get some film occasionally is in very rural centres or in dental. Sometimes in dental you'll get film, but because there's such little film about, we used to do 30 hours on film, film screens. We used to sort of teach that for 30 hours. And then another 30 hours on processing the chemicals and stuff. It used to be a big deal, but you guys don't have to worry about that anymore. So let's just talk about the digital image. Now, before we talk about a digital image, it's worth sort of thinking about what a natural image is. When we use film, the belief is generally that digital is good. That digital is good, that it's offering huge advantages. And it is offering advantages in terms of storing images. It's offering advantages in terms of transmitting images. It's wonderful that you could get x-rayed now in Sydney and have an expert in Harvard look at those images within seconds. That's an amazing thing. You can imagine how hard that would have been when we had film. So there are those sorts of advantages. The downside, though, is in terms of detail, digital is not as good. Film still gives better spatial resolution. I will define spatial resolution later on. But the bottom line is that film gives better spatial resolution. Now, how much spatial resolution? I'll talk a little bit about how we measure resolution and stuff in next week's class when we talk about image quality parameters and physical image assessment. But we talk about something called line pairs per millimeter. And what that means is if you've got and you can x-ray this sort of phantom, if you like, this sort of piece of plastic, which in it has got various levels of lines per millimeter. So if this is a millimeter, in this, for example, you have one line pair. A line pair is this sort of radio opaque bit and the radio lucent bit beside it. There's another, there's another, there's another, there's another. So that has 5 line pairs per millimeter. Okay. Now, obviously, if a system can resolve that, that's good. Film used to be able to resolve 10 line pairs per millimeter. Okay. It used to, and by resolve, I mean that you could clearly distinguish this line from this line, for example. It wasn't sort of blurred together. Okay. I remember we did an experiment 20 years ago. The student who did the experiments, now the Associate Dean in University College Dublin, looking after sort of medical students and radiography students. And what we showed in that study is that with the best eyesight, with the best film, with the finest focal spot size, the best that the human could see was 10 line pairs per millimeter. That was the best the human could see. Now, if you use magnifying glasses, fair enough, you can see more. But under normal circumstances, the best the human could see was 10 line pairs per millimeter. I remember then a book was published. It used to be the main book in sort of photography for X-ray students, for radiography students and radiology students and so on. And it said in the textbook 15 line pairs per millimeter, that we could actually see 15 line pairs per millimeter, and that film screen combinations could give 15 line pairs per millimeter. We wrote to the editors. We said to them, this is really worthless information because the eye can't see any more than 10 line pairs per millimeter. So why is it useful to be talking about 15 line pairs per millimeter? And we wrote to the editor and we designed a very nice, very polite letter. And in the 6th edition, that was the 5th edition, in the 6th edition they said the film screen combinations could show 17 line pairs per millimeter. So they went the actual opposite way to everything we were saying. But anyway, I can see 10 line pairs per millimeter. Good digital systems probably get you up to 7 or 8, you know. Whereas film had it, with film we had it at 10 line pairs per millimeter. Digital is probably a bit less than that, about 7 or 8. It's getting better and better then. Okay. So digital is good in terms of transmitting, in terms of storing. It gives you can process the image. If it was too dark, you can make it lighter. You can do all these things with it, and that's good. But it's not perfect. You know, there are issues with digital, and we'll talk about those. So if you can imagine a natural image, what a natural image is, and the reason why digital can never be as good as a natural image or with film, is that digital is about boxes. It's about putting a value into a box. It breaks the image up into boxes. So this part of the image has to have a different value than this part of the image. It's got to have a discrete, separate value. It can't blend perfectly from one into another. It's a discrete number. If it's 3, then it's different from 4. Even if it's 3.999999, that's different from 3.999998. There is a boundary there. There's suddenly a block. There's a difference. That exists with digital. It didn't exist with the natural image. And for example, if you look in this corner, and you can see here, for example, it's not a great example because the shades, yeah, maybe that corner's better. Okay, so what you see here is, I think we would agree that this here is slightly darker than this. We can see that this part of the wall is slightly darker than this, okay? However, there is no sudden transition there. No one can see, forget about this piece of building here, but if you can ignore this line, there is no transition there. There's no sudden shift from one brightness to another. It's a natural, continuous change. That's what the natural image can offer you. Digital cannot offer you that. Okay, it might try and fool you with different sort of processings and stuff, but it can't offer you that natural, gentle change. Because it has to have discrete values. It's numbers. You have to give it numbers. So once you start giving this a number, and we know that this is a different number, there's got to be some sort of barriers between these numbers. Okay. So with a natural image, we had this lovely continuous tone where shades and colors blended. With digital, we can't have that. And that's the first thing. I'm not saying it's a massive deal, but it's real. Okay? And it's the first thing to acknowledge with a digital image is that we are breaking the image up into boundaries and boxes. Okay? And that brings with it certain potential disadvantage. So to change a digital image, what we got to do is create blocks of brightnesses. So if again we look at a chest, okay, and this is your normal sort of analog image. Analog's just another way of saying film. With digital, what we've got to do is we've got to break it up into blocks of brightnesses. Okay, that's what a digital image is. Of course, with a chest, we're probably talking about 2,000 blocks this way and 2,000 blocks this way. Okay, with other images, you don't get so many changes. With a chest, it could be 1,000 to 2,000. The breast would be 2,000 by 2,000. A CT is often only 256 by 256, sometimes 512 by 512. Okay, so different images do have different types of numbers of blocks, if you like. So all we're talking about are blocks of brightness. That's all a digital image is. Okay, so to achieve these blocks of brightnesses, we've got to do two things. We've got to sample and we've got to quantize. By sampling, I just mean you create those blocks. You create those blocks. Okay, so you break it into how many blocks you think are appropriate. And we'll talk about how many are appropriate in a little while. That's where it gets a little bit more tricky. Once we've broken it into blocks, which is sampling, we've then got to give each block a number. We've got to give each block a number. That's quantizing. And the aim of that quantization is to represent the original piece of information in the original image. And that's what sampling and quantization is about. Most of our talk today will be about sampling and quantization. Because sampling determines your spatial resolution. In other words, how it's the ability to record changes through space. It determines your spatial resolution. Quantization determines your brightness resolution, how well you're recording the brightness levels within an image. So sampling is about spatial resolution. Quantization is about brightness resolution. Okay. You all know, and again I'm sort of talking very simple thing, that one of those blocks of brightness is known as a pixel. If you're talking about volumetric data like CT, where you've actually got depth, so it's actually a cube, it's known as a voxel as opposed to a pixel. And each pixel has its own address. And that becomes handy when you're talking about processing the image. If you want to extract things or segment the image or pull out things from the image, you know, those coordinates make it very straightforward. Okay. So, I don't know if this is going to work. Yeah, okay. So, for example, this is supposed to be, it's not, it's completely contrived, but it's supposed to be a non-digital image. Okay, it cannot be if we're displaying it with a projector, but imagine you can see that the sky, the sort of light sort of nicely going in a continuous way from one brightness to another. As you say, it's not really what it is, but it gives you sort of an idea. Whereas here, what we've got is suddenly, in this particular image, I deliberately only gave it about 8 levels of brightness, okay, which means that it could no longer shift continually across here. It had to jump from this value, and then had to jump to the next value, okay, and to the next value. And suddenly you can see lines going across that image, okay. That sort of thing, and I'll come back to that in a minute, is known as posterization. When you see those lines going across the image like that, it's known as posterization. Now, you know, and you see this often in the old sort of 70s and 80s musical videos. They used to sort of create these effects and stuff, which is not a big deal here. You can still see what you're looking at and so on. But imagine if this was a chest and you saw a line like this coming down the side of it. To me, that could be a pneumothorax. Okay, so this is a big deal in X-ray imaging. We've got to get it right, because these sort of lines, just as an example of a type of aliasing effect, could be disastrous in medical imaging. Medical imaging is the ultimate test, if you like, for digital. It has to be absolutely right. Otherwise, you're going to get stuff that's going to create misdiagnosis. Okay. Okay. And again, here's just sort of a thing about that. That one was about brightness resolution. This is about spatial resolution. You probably can't see it there. But on the right, we've got far more pixels in the image. You can see probably that that's clearer than the other one. Anyway, that's not a big deal. Okay, so today we've really got to talk about 4 main things. The first two will occupy most of our time. Three main things, if you like. The first two will occupy most of our time, spatial and brightness resolution. Don't forget that color is associated with brightness as well. Okay, color is the same as brightness, except you're talking about three different types of colors. Okay, and we'll go into that. And then the last bit is about resolution through time. We do a lot of dynamic imaging, whether it's angios or baryons or whatever, and it's about being able to resolve details through time. Okay, simply put, spatial resolution is the ability to resolve changes through space as they change through space. Okay. So in other words, in this chest x-ray, you know, if you drew a line across here, it's the changes that occur through that, across that line. Okay. Brightness resolution is the ability to resolve the correct brightnesses of an image. So that, for example, if this is your heart, and this is supposed to be white, and this is your lungs, and it's supposed to be more black, how able is the system to record those sort of brightness differences? Okay. And temporal resolution is about, if you went through time, how able are you to, for example, see the contrast flowing through the coronary vessels through time? Okay. So let's talk about the first of those, spatial resolution. Okay, there's a couple of slightly tricky bits here, so we'll just try and work through them. If you have any difficulties, just shout out. Okay, it's the concept of space. In particular here, what we're talking about is two-dimensional space, but of course with CT you could be talking about the third-dimensional change as well. And that's down to this final spatial resolution you will have in your image is down to two things. So spatial density is one. In other words, the ability to resolve detail in your digital image is down, according to that first point, down to spatial density, which simply means the number of pixels you have in your image. So spatial density is around pixel number. How many pixels have you got in your image? Because in breast, we need very, very, very fine detail recorded. We'll have 2,000 pixels by 2,000 pixels because we've got fine details that we've got to try and record. Okay? Each pixel, if you imagine, only records one detail. So if you've got a breast image and you've only got 4 pixels, you're only going to get 4 shades of grey. That's all you can do, 4 blocks of brightnesses. Okay? So with breast, we look at 2,000 by 2,000. Chest, I suppose more normally it will be 1,000 by 1,000 because the detail within the body isn't so demanding. Again, if you go down to, as I say, CT of the pelvis, you're probably talking about 256 by 256 or 512 by 512. So the number of pixels determine your resolution within the image, your spatial resolution within the image. Okay. However, and this is the important thing to be aware of, the temptation then is to think, and this is what the camera people will try and make you think as well, is they'll tell you, yeah, we've got this phone, this is a 5, they'll show you the phone and they'll say, this is a 5 megapixel monitor. It's a 5 megapixel, we're using a 5 megapixel detector in here. So what? So, that's part of the story. We're using, Mammo would be using a 5 megapixel monitors and 5 megapixel receptors and so on. If you imagine multiplying by 2 and a bit, by 2 and a bit, so around 2,300 by 2,000 something or other gives you 5 megapixels. Okay, 5 million pixels. But it also depends on everything else to do with the system. the brightness of the system. So I say, for example, so you X-ray my chest, you've got 1,000 by 1,000, that's perfect at the detector. But from that point onwards, things go downhill because they've got to get onto that monitor without degrading. You've only captured it on a detector. That's where the pixels are determined, if you like, at the detector. You've then got to transfer that information from the detector through the wires or Wi-Fi or whatever you're using onto the monitor. That's what optical resolution is about. It's everything else that can degrade the image. So whilst you can have the most beautiful detectors with the amazing amount of pixels, it's no good to you if the rest of the system is poor. Okay? So optical resolution is everything else. And obviously, the lowest of these two will ultimately determine the final quality. Even if this is really high, it's brilliant. If this is poor, your system's going to be poor. Okay? And vice versa. So the lowest of the above will determine your final resolution. Okay. Now, as I say, the other thing to mention is that the detail you need, and this is the question you should be asking. You shouldn't be asking for a simple solution, how many pixels do I need? You should be asking, what am I X-raying in this room, and what sort of disease things am I X-raying, and how many pixels do I need to actually resolve? How much spatial resolution do I need to resolve that patient's illness? So you have to sort of bear that in mind. But the other thing to bear in mind is it depends what you do with the image as well. Okay? If a human is looking at the image, I've just told you that all they can see is 10 line pairs per millimeter. So there's no point having a system that produces 20 line pairs per millimeter. The human eye can't see it. It's of no value. It'll cost a fortune and it's of no value. Okay? You could present, 10,000 pixels by 10,000 pixels, but what's the point if the eye can't see it? Okay. However, if you're going to a computer analysis situation, it's very different. And you will have all heard a lot of stuff about artificial intelligence and stuff, and we've got a program of research looking at artificial intelligence with breasts. And when the computer is starting to extract the information, then we're starting to talk about something else. We're no longer limited by the human eye. Although the artificial intelligence at the moment is limited by lots of things because it underestimates often the power of the human to actually interpret things. But the bottom line is, in terms of purely extracting features from the image, they can deal with far higher resolutions than the human eye can. Okay. So you have to think about the end point of this image. What are you going to be ultimately doing with this image? I got an abstract this morning from one of the PhD students for a conference, and it's a shame we haven't got more time because it would be wonderful for you to meet her. She's just finishing a PhD, but together we're doing stuff on artificial intelligence, and we've just published a paper which we just presented a paper at the Breast Screen Australia conference, and we actually won best paper at this conference. And what we're showing in this is I can flash you up an image, and this is where it gets very, very interesting. I can flash you up an image in 1/3 of a second. Now, 1/3 of a second is quicker than this, okay? It's far quicker than this. And I can guarantee you, and if we had time, I'd love to show you these presentations, but within 1/3 of a second, you're able to detect whether there's a cancer there or not, okay? You don't need 4 minutes or lots of scrutiny. The vast majority of the information is gleaned within 1/3 of a second. It's called the gist. Now, and then, we use the gist all the time. Like if you go out there, when you're driving down the road, we don't as humans read the road like a book, reading everything, because economically that would be, poor use of our time and our energy. So what we do, we have the ability to be driving down the road, but we can see things that are going on over here, and then when we're sort of distracted by them, we'll go and then use our foveal vision to actually get the details of what's going on. And that's how we work. We don't look at everything in the room at the same time. But if I'm looking over here, I can immediately see if someone's putting up their hands over here. We have this ability. But with the gist, it's this very rapid thing. But what we showed in this study was if you combine, what we showed in the study was that a woman gets cancer in 2018, okay? She has an image in 2014, okay? And if she's been screened, this is what happens. You know, come back every 2 years. So she gets an image in 2014. Her cancer, though, is only diagnosed in 2018. We go back to the 2014 films, and we get the experts to scrutinize these images at length, scrutinize them, and they see nothing on that 2014 image. Nothing. There is no hint. And you give it to as many people as you like, there is no hint anything's happening on that image that would have predicted that 2018 event. If I flash it up for a third of a second, you see it. Okay? So the 2014 image will actually create a signal in that third of a second. There's something odd about this image. We don't know what it is, and the human may not be able to actually work it out over a period of time. But if I just flash it up, you'll say that one's different compared with a woman who will never get cancer. Okay? And I think that's fascinating, you know, and that's called the gist. And if we combine that signal, that innate ability that we've completely underutilized, we got a grant for it this year, we put a larger grant in for it for next year. If we can combine that with the computer analysis to start extracting out in an intelligent way the relevant features that may be associated with it, because we can't as humans make it out. It's there, but we don't understand it. Then maybe what we have is a predictor of breast cancer. And what we've shown is, our preliminary data has shown that combining that gist with image feature extraction, we can predict cancer better than any of the current models. The current models are around, the best current models, if they look at, you know, your age, did you breastfeed, you know, all these, your history, your genetics, and so on, will predict up to about 70%. Our early data with this is predicting somewhere between 81 and 85% accuracy of those women who will get cancer. But I think this is such an exciting period we're moving into, where we can blend, and this is the mistake I think a lot of artificial intelligence systems are making. They're doing it just with the machines. What we have to do is blend the machines with the human innate ability, and therefore we'll get the best of both worlds. And certainly that's what we're trying to do with this experiment. But it's a combination of both these things. Anyway, I'm digressing. Spatial frequency. Okay. How much spatial resolution you need depends on the spatial frequency of the image. So if you got asked in an exam, you're not going to get asked in an exam this simple sort of question, you know, how much spatial resolution do you need? It's very tempting. You get people say, oh, we need 2,000 pixels by 2,000 pixels. You know, what you need is determined by the spatial frequency in the image. Once you know the spatial frequency in the image, you can then work out how many pixels you need, okay, to create, so that we don't lose information. So what is spatial frequency? That's in itself a bit of a hard concept. Okay. Spatial frequency, if I drew a line across this, remember now that these black lines, if you like, stop the X-rays, the white lines let the X-rays through, okay? So on the image, you're going to get black and white on your image, okay? So if I draw a line across this sort of black and white image, you can see that those details change through space, okay? You've got brightness transitions from black to white, okay? And if you look at any image, if you take a little bit of, again, if you look at a lung field, for example, what you've got is you've got ribs, you've got lots of lung markings and stuff within that ridge, you've got the edge of the heart, you've got the edge of the ribs, you've got the edge of the collimation. And again, if I draw a line through that, brightness change. The only reason you see anything in this room is because of brightness transitions. Because you're changing the transitions from one brightness of light to another is constant. If you drew a line across this, the reason I can see you guys is because of brightness transitions. That's all that visual information consists of, is brightness transitions. Okay, or brightness cycles, where you're going from bright to dark to bright to dark. So if I sort of plotted this here, for example, this line from here to here, and this is, if you imagine these are the dark, these are the white bits are the white bits. What you're going to have through distance, if you like, you're just going to get, it's going to start off bright, and then it's just going to go black, black. You're going to get a transition, something like that, through distance. Okay, and that's all a brightness. That's all a detail is. A detail, visual detail, is all about simply brightness transition. However, the rate of brightness change or the rate of brightness cycles can vary substantially. Okay, so for example, if let me just clear this up a little. Okay, so I've got ribs and I've got lung markings and so on. Okay, and I draw a line across here. And I plot that, okay? It starts bright, and then as I go through the lungs, it's up and down, up and down, up and down. This is simply, if you like, bright, dark, okay? Then it goes through the heart, okay? But suddenly the brightness transitions have shallowed off, okay? And I come out the other end into the lungs again, okay? So within an image, the brightness transitions change. You can get high transition rate. Obviously, this is a high transition rate, and so is this. And then you get this other low transition rate where not a lot's happening. Okay. And you can imagine that's right. If you imagine the lung fields, you've got all these sort of lung markings that are changing rapidly as you move through the lungs. If you did an X-ray of the wrist, what you would see is you get black, then you get white at the edge of the wrist, and then you would get lots of changes in brightness levels as you go through the trabecular patterns of the wrist, and then you come out the other side again. Okay, so it varies. Okay, that determines the number of pixels you need, because clearly to record this information, this part of the information here, the heart, you actually don't need that many pixels. Like one big pixel would almost record most of the information there. Okay. But because all the changes are happening here, you need lots and lots of pixels to record this high sort of transition rate. Okay, you need lots of pixels to record this high transition rate. So let me go back to my sort of line pair tool again for a second, because ultimately the question we need to ask, and this is all about sampling. Numbers of pixels is sampling. So here I need a high sampling rate. In theory, I don't need such a high sampling rate here, but I need a high sampling rate here. Now, how much of a sampling rate do you need? Sampling rate is simply number of pixels. How many pixels do you need? What is the sampling rate you need? Let me ask you a question then. If we're back here, okay, so we've got these line pair things, okay? I've just blown it up. And that is 1 millimeter. Okay, so we've got two line pairs there, if you like. Two line pairs. Just imagine a line pair is simply a radiolucent block of material and a radio-opaque block of material. Okay, it becomes a line pair. So, in other words, we've got two lots of detail here. This is, if you like, the detail. If this is a lung marking, this is what you would see. One lung marking, and then the next lung marking, okay? Because you'd have a space in between. How many pixels do I need to record that? How many pixels do I need to record those two lung markings? 2? 4? Well done. It's 4. Because to get that lung marking, if I just recorded there, and I just recorded there, what I would get, the whole thing would be recorded at that density. Okay? So you've got to get the detail plus the space beside it. You've got to get the detail plus the space beside it to see it. So in other words, for two details, you need 4 pixels. Okay, so for 2 cycles of information, you need 4 pixels. Another way of saying that, for 2 details or 2 cycles of information, you need 4 pixels. Okay? That tells you the necessary sampling rate is twice the spatial frequency. Spatial frequency is, sorry, I should have gone that first. The spatial frequency is how many cycles per millimeter. So you need 1 cycle. You'll have for this, it'll go, if we plot that. Okay, so this is, we're going to get, it's black, it goes to white, then it drops to black, goes to white, and so on. So there's 1 cycle there. There's another cycle here, okay, recording this piece of information and then this piece of information, okay. So what we need is a sampling rate that is twice the spatial frequency. The spatial frequency is how many cycles per millimeter. How many cycles are we getting per millimeter? I should make these a little bit more. Tried to draw that. Still not doing very well here with this drawing. Okay, so that's, this bit is representing this bit is representing this, okay? So each one of those is a cycle. How many cycles do you have per millimeter? That determines your spatial frequency. So your spatial frequency is how many times do we have a cycle per millimeter. Your sampling, the necessary sampling rate is that you've got to sample twice your spatial frequency to gather all the information. So in this situation where we have 2 details, we've got to sample twice the spatial frequency. We've got to sample twice the number of details within the image. Okay. Okay. And that's known as the sampling theorem. The sampling theorem tells us that if we want to record all the information, we've got to sample twice the spatial frequency. If we want to record all the information, we've got to sample twice the spatial frequency. So if there are 2 details per millimeter, we've got to give it 4 pixels. If there are 8 details per millimeter, we've got to give it 16 pixels if we want to record all the information. Okay. Any questions about that? Okay, so the sampling theorem tells us we've got to sample twice the spatial frequency to record all the information. So the highest, another way of saying that is the highest recordable rates equals half your sampling rate. Okay. Another way of saying that is if you've got 20 pixels in a millimeter, you can only record 10 cycles of information. If you've got 20 pixels per millimeter, you can only record 10 cycles per millimeter, because your sampling rate tells you that you have to sample twice the spatial frequency in your image. So if you know, for example, if a manufacturer comes to you and says to you, you've got 20 pixels per millimeter, you know the highest recordable rate is 10 cycles or 10 pieces of information per millimeter. That's known as your Nyquist rate. Your Nyquist rate tells you what is the highest recordable amount of spatial frequency you can have in your image. The Nyquist rate tells you what is the highest number of spatial, what is the highest spatial frequency you can have in your image. So there's a bit of jargon there, we'll go through it again. Nyquist rate simply tells you how much spatial frequency you record in your image. And the Nyquist rate is determined by simply the Nyquist rate is determined by number of pixels. If you know your number of pixels, you know that the Nyquist rate is half that amount. It's the highest recordable amount, because if you've got 20 pixels, you can only record 10 pieces of information. So the Nyquist rate is half the number of pixels you have. Any questions on that? So let's just go through that again just to make sure that you're clear. So a detail is simply a transition. When it goes from black to white, you've got a detail, or from grey to two different grey levels, you've got a detail. Okay? It's a brightness transition. What changes is the rate from what changes is the rate of transition. So in one part of the image, you could get lots of changes. In another part of the image, the transition rate becomes much slower. The sampling theorem tells you that if you've got 10 pieces of information per millimeter, okay, or 10 cycles per millimeter, remember a piece of information is a cycle, you've got to sample twice that amount. You've got to have twice as many pixels, okay? And that in turn tells you your Nyquist rate, because if the manufacturers come back and tell you you've got 20 pixels per millimeter, that means you can only have 10 cycles within that millimeter, or 10 pieces of information. Any queries or questions on that? All right, let's just keep going for a couple more minutes and then we'll have a break. Okay, high versus low sampling. You know, it depends on your application. So say breast requires huge amounts of sampling, CT doesn't, or MRI requires less, nuclear medicine requires less. So it's very much dependent on your application. The argument could be made, why don't we sample high all the time? You know, in case that we don't know what we're necessarily using this for, so why don't we have the maximum number of pixels all the time? Why wouldn't you do that? Why wouldn't you record an image with the highest number of pixels all the time? What is it? Say that again? Yeah, exactly. File size. If you end up with huge file sizes, it's a bit like when you're sending an image. It'll with message, you know, it'll ask you what sort of size do you want your image to be. It'll take ages to transmit. It'll take a huge amount of storage problem. It'll cost more. So you do try and match the number of pixels to your actual requirement. Pixel calculation is easy. Just do, you know, count the number of pixels horizontally, multiply them vertically. Spatial aliasing now. If you don't sample enough, you have problems. So if you sample too much, you have problems in terms of storage and costs and transmission and so on. If you sample too little, you lose information, because you obviously, instead of capturing all that change as it's going across here, one big pixel here is just going to give you one value. You're going to lose lots of information. But it's worse than that. It's not just about losing information. and losing high-frequency details, you actually corrupt the information with moire patterns. And a moire pattern is something like this, okay? That if you have too few pixels, you undersample, what you can get is the computer trying to assume it knows what to do, and you get these beautiful patterns. Here, for example, there is no problem. The spatial frequency per millimeter, imagine this is a millimeter, the spatial frequency is fairly low. But as you move in here, the spatial frequency gets higher and higher and higher. There are more changes per millimeter. And when you see that, there aren't enough pixels here to handle that, you get this moire pattern. Again, it's not a big deal necessarily if you can recognize it as a moire pattern, but when this isn't a very good example, but when you get these sort of streaks going across a skull, or you get lines, strange lines appearing in a chest, it can mimic things that are wrong with the patient, and that's where it becomes a disaster. Okay, so moire patterns are where you undersample, where you have too few pixels. Finally, final details on spatial resolution, and this is just clearing things up. Viewing geometry. The amount of detail you see and the amount of pixels you need depends on the size of the image. If you go in to watch a film in the cinema, if it's a digital projected film, you'd need far more pixels if the image is this size than you would if you're watching it on a small computer. If you've got a big screen at home, you'll need more pixels being projected than if you're just watching it on a computer. It also depends on the distance. The closer you are to looking at something, the more more pixels you need. Interestingly, for those who are into sort of image perception and so on, the vast majority of people look at a computer at 60 centimeters. So they're usually at this sort of distance when they're actually looking at a computer, so therefore you try and create sort of the numbers of pixels that suit that situation. Aspect ratio is simply the shape, and you know this, is the shape of the image. That would be a 4:3 aspect ratio because it's wider than it is deeper and so on. You can get square images, but they're pretty rare. And depending on what we're dealing with, if we're dealing with a chest, we still probably have an aspect ratio of 3:4. So it depends again on what you're looking at. Okay, we'll move on to brightness resolution after the break. The key thing you must understand at this stage is about sampling, it's about spatial frequency, and it's about the sampling theorem with Nyquist ratio. Anyone any problems with that, we can talk about it. So it's now 11 o'clock, so if we come back at 10 past, and we'll start on the brightness stuff. Yeah.
In that is just one bit of information.
Yeah, okay, so what I'm saying is that this is 1 millimeter.
Oh, that's...
So 1 millimeter, sorry, yeah, I've got 1 millimeter here. Okay, so in this millimeter, we've got 2 pieces of information.
Oh, okay, yeah.
So you've got 2 cycles. Okay, so you'll
Is
need
that
4
from
pixels.
Trough to peak? Or
Yeah,
don't think of it like that? Or?
Yeah, I was just trying to make it as simple as possible. So if you can imagine, it's
like darkness.
dark, bright, dark, bright.
Right, okay. So there's 2 bits of information in that 1 millimeter. You could have 4 though.
You could have 4 pieces of information in 1 millimeter, but if you
need 8.
Correct. Yeah, okay, yeah. Hi.
I just wanted to know, Nyquist rate, is that just synonymous with spatial frequency? So Nyquist is the maximum, but
Yeah.
it's just another term.
Yeah, no, it's not really, because if you think about spatial frequency, it's spatial frequency. I often think about spatial frequency of what's in the body. So if you've got in a wrist, you've got a certain amount of changes going on, okay, and what you're trying to do with digital is trying to reproduce those changes.
Yeah.
So spatial frequency within the body would change maybe 20 times per millimeter.
Okay.
If it does, and you've got 40 pixels to reproduce that, then your spatial frequency will equal your Nyquist rate. because your nyquist rate will have 40. If you've got 40 pixels, you can record 20 pieces of information. So if this is your spatial frequency within the body, then you can actually reproduce that. It equals your nyquist rate if you've got enough pixels. If you haven't got enough pixels, then your nyquist rate will be less than the spatial frequency actually within the patient. Does that make sense?
Yeah.
Now, another way of looking at this would be if you suppose that I took a picture of your chest, okay, and I've got a monitor over here, okay, that has, say, 1,000 by 1,000 pixels, and a monitor over here by 2,000 by 2,000 pixels. The spatial frequency within your chest image could be, you could have 10 changes per millimeter. But the nyquist rate, because it's going to be different on the two computers, even though the original image has got 10 line pairs per millimeter or whatever, the nyquist rate over here with a higher res computer is going to be different from this, even though it's the same original image. Okay. So it depends on the nyquist rate simply depends on the number of pixels that you have available with the particular viewing system, and it's half that number.
Can't be spatial frequency, because that will depend on how many pixels.
Exactly. It depends on how much information in the original information, in the image. Yeah. So,
Just a quick question about this. The brightness circle, is that we just need the highest part there and apply to the whole image?
yes. Yeah.
Okay.
You're not going to have. Yeah. You're not going to have in one sort of receptor. You're not going to have varying amounts of pixels to suit an image. So what you do is you find the highest. You go for the highest one, and when you've got the highest one, you know you've reached the highest standard you need for that image. Yeah.
Okay. This is the image.
Oh yeah. Thank
the
you.
film frame.
Oh, well done for doing this. Yeah.
Did you see the fracture?
Yeah, I did. Yeah. Now, I think your problem is here in this particular one. Your problem is that this is getting too pale. You know, it's not a question of the actual brightness distribution of the bone, but what you've got is this is perfectly exposed here and perfectly.
Yeah, because it's the hand X-ray, but we noticed something there.
Yeah, well, they did well to notice it because it was hard to see. But I think the reason you're seeing it better is just that happens that the brightness levels happen to suit this a bit. You've got, you know, here you almost reached a washout period. You know that this is you couldn't diagnose anything with that sort of brightness level. You know.
Yeah.
So it's
We
not
do
a
have
case of
another view,
reversing.
lateral view, we can see it better. But
And the other thing is, it's obviously a child, but I wouldn't have thought that's a green stick fracture.
oh, it's a transverse fracture, yes.
It's a transverse fracture, not a
Yeah.
green. Not, it doesn't look like a green stick
No.
fracture.
Yeah, we got another lateral view.
Oh, okay, right. Okay. No. I think you're right. In this, you can see it better here, but I don't think that's because of reversing. I think it just happens that we've washed out the image here.
Oh, really?
Yeah. Okay.
Asked our doctor, and he say he usually will invert the color, but to find like long more nodules.
Yeah.
And I find that there is actually a paper to support that idea.
Yeah. We wrote it.
Oh, really?
It's John Robinson.
I forgot the name. I haven't go through.
Have a look at the paper. Yeah, John
Okay.
Robinson and I wrote that paper. If it's the one I'm thinking of, lung nodules one. Yeah. British Journal of Radiology. Yeah, I think so. Yeah.
Oh, thank you.
Okay, righto. All right, let's keep going. All right, so what we've talked about so far is that the digital image you have to talk about the digital image in terms of spatial resolution, brightness resolution, stroke color, and temporal resolution. What we've talked about so far is spatial resolution and how well can we record changes through space. So remember, a detail is simply a brightness change through space. How many brightnesses determine how many pixels you need. So moving on to brightness resolution. With this situation, what we're talking about is the ability to produce gray levels. So now we know how many blocks of brightnesses we need, because that's determined by your spatial frequency. What we're trying to do now is work out what brightness level do we need to reproduce the original information. Now, there are two terms here that are used synonymously, and they're not quite synonymous. Intensity refers to a real situation. So when I look at you, you guys are fairly intense. Okay, this is a fairly sort of real situation. Okay, brightness refers to an image. Okay, so just be aware of that subtle difference. Okay. So we've broken the image into blocks of brightnesses. We've talked about the sampling. What we now are trying to do is quantize each of those blocks. Give those blocks, each of those blocks, a particular gray level that will be able to reproduce the original information as well as possible. Okay. And that all comes down to bit number. How many gray levels are we going to make available to each of those pixels? Okay. So if we only make 2 gray levels, black or white, okay, that's a 1-bit system. A 1-bit system will give you 2 gray levels, black or white. The switch is on or off, okay? It means that what you would have here is simply a black or white image. You would lose loads of information. It would be very, very contrasty. Remember right at the beginning, we talked about what is the ideal contrast of an image, and I said to you, be careful about saying very high contrast is always good, because that is the ultimate contrast, is black and white image. But you're going to lose all the subtleness that lies in between. And indeed, the vast majority of the pathological information is in those subtle grey levels as opposed to the black and the white. Okay. Now, for those who are not aware of bit numbers, I'm sure you all are, but just to get it out of the way, 1 bit, if you can imagine, it's like a switch. A switch can be on or off. Okay. So 1 bit gives you 2 options, on or off. Okay. 2 bits then gives you how many options? If you have 2 switches, how many states can you have? I can hear it somewhere. 4, yeah. It can be, and if I'm not going to go through all of this, for all of these sort of options, but if you can imagine, it can be, if you have 2 switches, it can be on, off, off, on, off, off, on. So you've got 4 options, okay? If you've got 3 bits, how many options have you got? 6? 8. Correct. Well done. 8. 4 bits, you sort of double it each time. 4 bits, 16, and so on. So 8 bits gives you how many options? A typical imaging system's got 8 bits. Usually, you know, apart from nuclear medicine, the vast majority of imaging systems will have at least 8 bits. How many grey levels do you get with 8 bits? 256. That means you now, if this is an 8-bit system, you've now got any value. You can give each of these pixels any value between 0 and 255. Okay, you can give it any values. The more values you make available to it, the more able you are to record those subtle differences within the patient. Okay, so an 8-bit system will give you 6 values, 9-bit 512, a 10-bit 1024, and so on. Okay, and that's what I mean by the concept of bit number. The number of bits determine how many gray levels you're going to make available to each pixel. Okay, and then each pixel can choose the one of those 256 gray levels that best suit the original information. And obviously, the more gray levels you have, the more able you are to differentiate between the different parts of the body. Okay, pull out those subtle differences. The dynamic range is simply another way of saying how many gray levels have you got available. Okay, and that's all you need to know about gray levels or brightness resolution. Okay, it's simply how many gray levels are available to each pixel. The more gray levels you have, the better able you are to resolve any brightness in the original image pertaining to that spatial area. Okay, a couple of extra things here. Brightness contouring we've talked about. This is brightness contouring. When you haven't given it, in this system we've got an 8-bit we've got 8 gray levels. It's a 3-bit system, this image. Okay, there's only 8 gray levels available to it, and therefore when it jumps from this to this, it does it in a very abrupt way because it hasn't got 256 gray levels to choose from. Okay, it's only got 8 colors to choose from, so it jumps from this to this. Okay, I'll differentiate between color and brightness in a minute. That's known as contouring or posterization. Okay, so brightness contouring, you get these contours in the image, and as I say, that can look pretty menacing in a medical image if you get that sort of change going on in a kidney or something. So we've got to try and avoid it, and that happens when we've too few gray levels available to us to a too low a bit number. Bit plane, now I'll sort of explain it to you. I think it's fairly useless information, well, to a certain extent, but you'll see it referred to. If, for example, 1-bit gives you 2 gray levels, 2-bit gives you 4 gray levels, the 3rd bit then gives you 8 gray levels. The addition of the 3rd bit gives you 8 gray levels. How many extra gray levels did the 3rd bit add to the system? Yeah, 4. It's as easy as that. 4. So in other words, the bit plane is the additional number of gray levels that a bit will add to the image. Okay? So for example, you've got, just to run over that again, if you looked at, if you imagine that with 4 bits you get 16 gray levels, but the 4th bit added 8 gray levels, because with 3 bits you only had 8. Okay? So by adding the 4th bit and getting 16, you've got an extra 8 levels, and that's what we mean by bit plane. Now, bit plane is where it could be useful is in compression, because if you work out which of the bit planes are least useful to you, you can pull that out of the image. But I wouldn't worry too much about it. Just be able to recognize what it does. Logarithmic digitization. Our eyes see logarithmically. Okay? In other words, if you told me that you think that this here, in your eyes feel that this is twice as dark as this, okay? If I actually measured that, okay, you're telling me this looks twice as dark as this. If I actually measured that with a densitometer, this would be 10 times darker than this, okay? That's the way that our eyes see, okay? We may think that something is twice as dark as another, as one gray level is twice as dark compared with another gray level. But in reality, if you measured it, the darker one would be 10 times darker than the lighter one. That's just the way that we see. So it incorporates that into the into digitization. So if you see a gray level here, for example, okay, say this was here, had a gray level of, I don't know, 200, and this area here, this white area, had a gray level of 100, okay, if we actually measured that with a densitometer, we'd find that that would be probably 10 times darker than that, okay, just so it matches the eye. Okay. Number of bits required, you now know that that's not an easy question to answer. We don't know. It depends on what you're looking at. For breast imaging, we will be talking about a 10 or 12-bit system. For chest imaging, probably a 10-bit system. For nuclear medicine, we often go down maybe only a 6-bit system. You know, nucleus medicine's about not the subtle grays, it's whether there's a brightness there or not. Okay, so the number of bit depends on what you're looking at. So if you ever get asked that by anyone, you know, is how many bits do we need or how many pixels do we need, it depends on the original information. And we talked about this perceptual linearization last week. Okay, does anybody want to remind me what perceptual linearization is? Correct. So it's your ability that if you're struggling with seeing something, you'll naturally go into a bright room or under a bright light because you can detect subtle differences more easily when the image is bright compared with when it's dark, even though the absolute grey change may be exactly the same. You know, if you look at a pixel value, a low pixel value of 10 to 12, for a pixel value of 10 versus a pixel value of 12, and you compare that with a pixel value of 240 to 242, even though the change in numbers is exactly the same, okay, you'll spot this one much more easily than you'll spot this one because this one's dark, okay, because it's got a low pixel value. And therefore what we do is we perceptually linearize, we exaggerate. So when we display the image, remember the last stage of that processing sequence we talked about last week, the last stage of it, we perceptually linearize. So in fact, when we display it, we exaggerate this change. Okay, we apply an algorithm that makes this change visibly more obvious to equalize this sort of, or normalize this sort of natural ability to perceive things more clearly in bright parts of the image. And if anybody's into that, the guy did his PhD in this area, and it's one of the most famous models within medical imaging perception. It's called the Barton model. He never published anything. We've never heard of him since. But this was his PhD, and it has transformed the way that we look at all the medical images and how they're displayed. Okay. So perceptual linearization is trying to make up for this, our eye's ability to recognize changes here more easily than here. Okay. And that's really all you need to know about brightness. Brightness is simply trying to reproduce the gray levels in a way that will actually see fine details that represent disease or anatomy. Okay. Related to brightness is color. Okay. Color we don't use too much of yet in medical imaging. We do a little bit in ultrasound and stuff, but most of our images are monochromatic. Monochromatic simply means the black and white. Okay. So, but with color we have trichromacy. With color, everything you know about brightness applies to color. Okay, so everything you know about brightness in terms of number of bit levels for each pixel and so on applies to color, except there are usually 3 colors, trichromacy. Okay, there are 3 colors, and you've got a pixel value for each color. Okay, so each of those 3 colors will have its own separate pixel value. So if you look at a monitor close enough, you actually get down there with a microscope, you can actually see that there are three, for every pixel, there are actually three different colors that you can light up. Okay. To display color, you've got two choices. So if you look at a color image, you've got two choices depending on whether you're looking at a monitor or whether you're looking at printed material. Okay, whether you're looking at a monitor or you're looking at printed material. So, how many colors can the eye see? How many colors can our retina actually recognize? So I'll take any number. How many? 3. Well done. Who said that? Yeah, well done. 3. Which colors are they? Well done. They're the only colors the eye can see. You may see that this girl has sort of a turquoise sleeves or a brown jacket or whatever, but the only colors that the eye can recognize are red, green, and blue. Okay, they're the only cells we have in the retina that allow us to pick up color. Okay, so we can recognize red, green, and blue, which presents an interesting situation. How on earth do you display the array of colors that we have in this classroom if we've only got red, if our eye can only detect red, green, and blue? Okay. Now this will, what I'll say to you in the next few minutes will confuse you a little, okay? So just be warned. Okay. So you'll recognize this. Anyone who's done sort of biology and stuff will recognize this. Red, green, and blue. Okay. So the retinal cells can only recognize those. So it's a case of blending. So some of the information about red, the red cells will be stimulated by a certain amount, and maybe a little bit of the blue cells, and maybe loads of the green cells, okay? But this will then allow us to see different colors by relative stimulation of the red, green, and blue. So what does red and green give you? What color will red and green give you? And please don't think about mixing paints. It doesn't work. Anyone? Red and green will give you brown. Everyone agree with that? No, it's nonsense. Red and green. Orange. Nonsense. Yellow. Red and green give you yellow. Well done. Yellow. Okay, red and green gives you yellow. Okay. What will green and blue give you? Okay, green and blue. We haven't got that many colours left, I don't think. I'll take red and blue if you prefer. Purple. Again, you're mixing paints. Red and blue, if you stimulate the eyes, the red and blue sort of the retinal cells, what will you get? Pardon? Brown? It's gone, I'm afraid. This is the sort of thing you learn when you're children and you can't remember. These are, by the way, to give you a clue, these are the secondary colors. These are the primary colors. These are the secondary colors. Okay, so what are the secondary colors? Orange? Yeah? No. Anything left? Yep. Pink. Afraid not. Anything? Black. black, actually, I'll tell you what about black later, but it's not relevant here. Yeah, yeah. Okay, anything else? Purple? Okay, I better put you out of your pain. Red and blue will give you magenta. And green and blue will give you cyan. Yeah. Okay. Now, the important thing is that monitors and TVs will use the primary colors. The printing industry will use the secondary colors. Okay? Okay, secondary colors. But it means that when you relatively stimulate these in certain ways, you get these different colors and so on. Okay. This middle bit, when you get all colors together, gives you what? Everyone thinks black? White. Think about the sun. The sun's light has all the colors in there and everything is white. Okay. 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 Right, so in the monitor industry, each pixel has the ability to display red, green, and blue, and then it can create these other different colors depending on the relative stimulation of those colors, so the relative presentation of those colors. Okay. Right. Now, however, it gets the easy bit. In the monitor, we add the colors together, the red, the green, and blue. We add them together, and we get a certain color. In the printing industry, we use subtraction. Okay. What does the secondary color? If this is the secondary color yellow, its primary color is blue. It's the opposite one. Okay. So the secondary color of cyan, or the primary color of cyan is red, and the primary color of magenta is green. Okay. If you print something, okay, imagine, just believe me for a moment, this is cyan. Okay. 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 If we put cyan on there, okay, if we put cyan on there, what is the subtractive process? What color does it pull away from the light so you can't see it? So that if you put cyan on there, if you actually spray cyan on there, it will pull out of the red, green, and blue a particular color that you can't see it. It'll absorb it. Correct. Okay. By putting a secondary color there, you subtract the other color. Okay? So then your eyes are only stimulated. So if you've got your secondary color, it subtracts the primary color, it absorbs the primary color, so your eye is only stimulated by the green and blue, which will give you then your cyan. Okay, now get your head around that. So the secondary color subtracts out of the light, because the reason you see that is through a reflection of light. Okay, that's the only reason you see that, is light reflecting on that. If that is cyan, it's pulled out the redness from the three colors you could have seen. Okay, it leaves you with the green and blue, so your eyes will be stimulated with the green and blue light. Okay, that's emerging. And then, because it's green and blue, the only color you see then is cyan. That's how it works. Okay? You see cyan because you're simulating green and blue. Okay, because you've pulled out the red. Some of you are going, oh, but I don't believe you. I believe you're finding this. Okay, just remember that a secondary color pulls out its primary color. Therefore, that leaves behind only the other two primary colors. Your eyes stimulated. When you get those two primary colors stimulated, you get the cyan, because you can see the overlap here going on. Okay. So let me say, if that drinking drinking bottle was yellow, okay? What happens? What's happening to your eyes right now? The white light's hitting it, white light's hitting it. So, yeah, correct. Well done. That's absolutely right. Yeah, good. That's fine. All happy with that? You're going to have to just think it through. It's logical, but you've got to remember that diagram. That diagram is important because you won't be able to work it out otherwise. Okay, so that's the subtractive process. Okay. Okay. The last thing then we'll do today is the temporal resolution part. Okay. Temporal resolution is about, sorry, yeah. Please don't worry. Yeah. Why do they say? Yeah. Yeah. I have no idea. I have no idea. And in fact, I think they use the black because it's cheaper, but in fact you'll get black. Because what I didn't tell you was that if you mix the secondary colours, what's going to happen? What light is it going to absorb? It's going to absorb all the colours. So if you mix the secondary colours together, it'll absorb all your primary colours, so you see black. But it means you have to use 3 lots of ink. Yeah. Okay. So temporal resolution is about changes through time. So you give someone a barium drink. How well are you recording the barium as it passes through the esophagus through time? Okay. If you just take the odd second, you're going to miss parts of the anatomy. You're going to miss parts of that journey. So it's about frame rate. How many frames are you making available to the image to be able to record these temporal changes? And clearly this is not just about digital. This was equally relevant with film as well. It's about motion accuracy. With normal TV, we usually think that if we get above 25 frames per second, we'll see things in a fluid way. Our eyes will merge those individual frames together so we see things fluidly. If we get less than 25 frames a second, I think the number is actually 23, but say 25 frames a second, you'll see a sort of jerky appearance as you move from one sort of section of the anatomy to another. Okay? So usually if you try and get 25 frames a second, that's usually enough to see a relatively fluid sort of amount of information. If you don't, you get temporal aliasing. If you don't have enough frames a second, you get temporal aliasing. Now, and you have a sampling theorem. Basically, temporal aliasing can fool you, and I'll give you an example of that in a moment. Sampling theorem is just as relevant here. So, as it was with the brightness resolution, if you've got, if your heart is beating, say 60 times a second, okay? 60 times seconds, if you like, equate that to a brightness cycle, 60 each cycle, okay? How many times do you need to sample that? So 60 times a minute, how many times do you have to sample that a minute to capture all that information? 120. If you sample only 60, what your heart will look like is this. Okay? Because you'll have missed the other part of it. Okay? So you have to sample twice the motion that's occurring within the system you're looking at. You've got to sample twice that amount. Now, for example, with a child, you can have the heart beating up to maybe 120, 150 times a minute. Therefore, you're going to have to have 300 frames a minute. You know, so it depends on what you're actually looking at. But the sampling theorem applies here. You've got to sample twice the motion rate to get all the information. Now, as well as capturing the motion, there's another thing here called flicker. When you look at your iPads and you look at your computers, even though you're looking at the same image, it's not a motion image, it's the same image. It's not a case as if they've just put that image on there and it stays there. They're constantly refreshing that. It's refreshing usually at a rate of around 50, 72, 100 times a second. They're constantly refreshing that image. That's not just sitting on there like a picture, okay? It's changing every 100th of a second or whatever. And this is known as the frame rate. Now, if you don't have enough frames to demonstrate your image, you'll get flicker. You'll see a flickering happening. Now, the best example I had of this was years ago when I went to buy the old cathode ray tube type of TVs, which are not that long ago. Flat TVs have only been around for the last decade. But I went into the shop. I was sent out with only so much money, and I went out to the shop, and you had the 72 hertz TV here, 72 frames a second TV here, and it looked beautiful. And it was, I think it was 600 euro at the time. And then you look at the 100 frames a second TV at a 1,400 euro, and it looks beautiful. Then you go back to the 72, and you can see the flicker. You know, and it's a disaster. You know, so the fool I am obviously bought this one over here. You know, still got serious trouble. I'm still getting into trouble over it, but it's the sort of thing that that's what that means, is how many frames per minute, per second are you actually refreshing the screen. And you can progress an interlace scan. For those who are interested, it really doesn't matter here, but progress basically means where you look at every line in turn, you write every line in turn. Interlace means you do line 1, 3, 5, 7, 9, and so on. Then the next scan has 2, 4, 6, 8. So it's sort of an interlace sort of appearance when you put the when you're refreshing these images. And I think that's temporal resolution. It's a different world. When I finished my PhD in the early 90s, I remember film was everywhere. Film, chemicals, dark rooms were everywhere. You had to design X-ray rooms around this central massive dark room. And I remember going, after I finished my PhD, I got an interview in Belfast, and things were pretty horrible in Belfast at the time. And I also had an interview in Dublin. And I remember going to when you're going for an interview, you always go to the place, you know, to sort of let them know you. And before the interview, you sort of let them know you and ask all these questions that you've contrived in your head that you think they may be interested in you asking. But I remember that I went to Belfast, and there was this wonderful woman who I got to know very well later on. But she was the professor in charge of medical imaging in the University of Ulster. And she was a very large woman. And that's important to the story, okay? She's a very large woman, okay? And so I was asking about student projects and about the curriculum and stuff like this. And then I said, I'd love to see your equipment and your labs and so on. So she brought me into the X-ray room, and then, of course, into the dark room. Now, dark rooms, you may just think it's like a door that you open and you go into a dark room. That doesn't work, because as soon as you open this door, light floods in and fogs everything that's in the dark room. So you can't just have a door. So you had these theses written on how you entered into a dark room. So you could have this sort of door where it was locked and you could only go in when you pushed a button and so on, or you had a sort of a passageway that you opened this door and then you closed that door and you went in this door and so on. But the one that I'd never seen that she had, and I'd never seen one, was a metal cylinder, okay? So the metal cylinder was such that, if you can imagine, if I can remember it, it's a bit like you had the wall, then you had this metal cylinder that was a bit like this, okay? And inside you had this inner cylinder with an opening. So you walked through here, you then spanned this round and came out into the dark room. So this is the dark and this is the light, and this made sure no light, because all you needed light in there for a fraction of a second, everything was ruined, you know. And so, so she said, so she went into this room, so her and I went into the room, and she disappeared into this environment here, which I had no idea where I was going. I'd never seen one of these things before. So I jumped in with her, not knowing what was happening. But we did, in the room, the total space is about this sort of space here. So we span together through this cylinder, and we fell out into the darkroom, and that's it. But it was really good for me, I tell you. But it must have been good for her as well, because she offered me the job afterwards. But anyway, that's what darkroom. We had this ornate, complicated darkroom processing thing that we all had to learn, and sadly, you don't have to know anything about it anymore. But right. So next week we haven't finished this. So next week, what we're going to talk about is characteristics of a digital image, how you actually plot a digital image, and some Fourier transforms of the digital image, which we'll talk a little bit more next week. And then we'll get into image analysis and stuff. Any questions or queries on any of that stuff? Okay.
What happens when you put yellow, magenta, and cyan here and here?
Yeah, if you put that, which essentially is what you're doing in the printing industry.
Yeah, yeah.
So you got cyan,
Yeah,
magenta,
yeah,
and yellow.
yeah.
What you get here is black, okay, because it's going to absorb everything. If you've got these two, the magenta, if you work through it, magenta will absorb.
The green light.
Okay, so the green's gone.
Yeah.
The yellow will absorb.
Yellow, blue,
Yeah, so that leaves you with
red.
that will. So that has to be red, and vice versa. Yeah, because that's the only. Once you put, that's the way the printing industry works. Once you spray it with this and this, it takes out the green, takes out the blue, and it leaves you just with the only thing your eye can be left with,
Yeah,
which is
yeah,
red.
Yeah, yeah. The reason I'm asking is because I keep thinking back to the art classes we had in school.
Yeah, yeah, yeah. Hi. Yeah, what the machine will try and do, before you adjust it, the machine will try and adjust it for you because it has lookup tables. So it takes those grey levels, all those values that it receives from the initial X-ray, and then it will adjust those, because you've told it it's a chest X-ray or this X-ray, it will adjust that and it will give you the grey levels, depending on how many bits are available. It will give you the grey levels that it thinks you want to see. And then after that, if you want to further change it, you can do that. But I'll be talking a little bit about processing next week. Yeah, yeah. No, you can't change the pixel. The pixel, remember we did that thing last week, for processing images and then pre-presentation images and so on. Those for processing images are the pixel values that don't come from the paper. That's the raw image. But then what you do is you change those values depending on what the machine does it automatically for you to begin with. And then you further, if you want to, you further change those values. You will never change the original pixels coming from the patient. They're for processing images. But what you display, those brightness values, you can change. Yes. Yes, correct. Correct. Yeah. same. Unless you reverse. Unless you reverse the image. Yeah. Okay, right. Okay. shame you guys don't have much longer courses, you know, because we could cover all this stuff with you.
I did visual neuroscience.
Oh, did you? Well, then you know, you know.